Hello, everyone. Welcome to the second episode of Iron Digital of 2024. And let's dive straight in. Okay, so uh, to dive straight in, I actually need to switch the studio to sharing my screen. Okay, so as a reminder, we are inside a fascinating arc of targetable consensus. So, kind of like to catch up with previous episodes, we started with saying that, hey, the logical model of our database is a sequence of events. To realize this logical model physically, we recast it as a replicated state machine, which basically means that we have like the same sequence of events, but every once in a while, we are going to snapshot the events and say, hey, kind of like now our state is this snapshot plus whatever events are applied on top of the snapshot. And we are going to run this snapshot plus tail of events thing on several machines in our network. Then we discussed consensus, that if we have different machines in the network, obviously, if you want to kind of like do this replicated state machines, they need to run the same deterministic code. But even above that, because connectivity is spotty and machines might not always be able to talk to each other, we need some mathematical algorithm to make sure they share the same state. So we kind of discussed how you could solve consensus mathematically, which in a very simplified form is the problem of agreeing on a single value. Then finally, in the last lecture, we started discussing pragmatics of consensus, how to take this abstract algorithm about agreeing on a single value and arrive at a pragmatic, practical approach for actually implementing distributed state machines. And to that end, the situation is as follows. Each machine maintains its local log of events. And it also maintains a current view. Each view has a primary, and the primary is a machine that decides which events go into the log. So kind of like primary appends new events to its local log, and then it broadcasts events to other replicas. And those replicas, after we receive the event from a primary, well, we call this event prepare, they kind of like append it to its own log. And kind of like periodically, if the primary goes down, a different view is started with a different primary, And that primary then collects information from the previous views. It makes sure, crucially, that all the previous views are completed, that they are shut down, and they can no longer process any other prepares. And then it continues. So one particular optimization that we were looking at last time was pipeline. So if you recall, in the constants, there is like this pipeline prepare queue constant, which says how many prepares a primary is allowed to keep in flight. So roughly, when a primary accepts a request and replicates this request across backups, it needs to wait for a certain amount of confirmations. It needs to wait until, well, a quorum, like I will very carefully not say majority because we are not actually doing majority, but that's for future lecture. Well, maybe actually even this one lecture, but anyway, it needs to make sure that the quorum of backups actually receive this prepare and persisted it on the disk. And only after that, the primary can go and consider this prepare as committed. And the trick is, while commits have to be done in order, because in our state machine we have this very strict guarantee that, like, for any two transactions we know kind of like a specific order in which we are executed. This part where we broadcast prepare across backups and with information can actually be pipelined. We may prepare like 5 prepares in a row, and maybe we like first receive information from the third one, then for the fourth one, then we receive confirmation for the first one and the second one, and like when we receive confirmation for the first, we commit the first. When we receive confirmation for the second, we commit the second. And at that time, we already have confirmations for the third and the fourth one, so we can proceed and commit them immediately without actually. Okay, there is something disturbing happening here because I'm not sure if I'm actually streaming because, okay, Twitch shows that I'm offline. I'm not sure what is happening here. Okay, sorry, it looks like I frozen for a moment. I don't know why it's the case. Let me check if, like, I have internet connection here. Well, okay, it was fine here. Anyway, even if I drop out, don't worry. These videos are also uploaded to YouTube, so you will be able to watch offline. And it's not like it's important to watch online if you're not asking questions. And you are not asking questions, but like, please do ask questions in the chat. That's why I'm here. Where was I before I got partitioned out? Well, yeah, we have pipeline. So while the primary commits messages in order, it can actually wait for a replication in parallel. And let's maybe take a second look here how this actually works in the code. So let's go to our replica. And here there should be prepare case somewhere. Somewhere should be prepare case. Okay, yeah. So in the pipeline queue, what we actually store is prepare, and prepare is a message plus a bit set of prepare case from a replica. So we have this pipeline with quorums, and as soon as quorum completes, we are ready to committed prepare, and we actually committed prepare as soon as we committed all the previous prepares. So looking at again on prepare OK. So once we received the quorum, we actually go and start commit process. And then in this commit process, we will try to find if we have something in the pipeline. So yeah, kind of like if we have prepare and it has a quorum, and we committed all the prepares before that, we actually go ahead and continue with committing this prepare. So what's interesting here is that like repo tests, like they have their local log, but because of this pipeline, log is not necessarily contiguous. Like so, imagine you're a replica. So you might have received op equals 5, and then like op equals 7, and then op equals 8, and then only later like you have like this hole in your log, and then you have like op equals 6. So this is what has happened. Like your whole your log generally has holes, and one reason why that is the case is pipelining. Today we are going to look at the second reason why your log might have holes and how you deal with that. And that reason is disk errors. So, and this is kind of like really one of the core features of pragmatics of Taggable and what kind of like distinguishes it from other systems. So yeah, in consensus algorithms, generally you assume stable storage. You assume that once you've written something to disk and receive the confirmation from disk that the data is written, the data stays there. So if you crash and then restart, whatever you wrote to disk before is still there. This actually is not the case. This is not true. Like at scale, with many disks, some disks fail. Like sometimes you like write data to disk, and then this data is no longer available. Like maybe the entire disk is gone. That's possible. And then, well, kind of like you need to reconfigure to install new replica. That's in some sense like the easy case. The hard part is that maybe like this particular like area on disk where this specific data was stored got corrupted. And like, well, you need to do something with this. And the thing is, like with consensus algorithms, you actually are not allowed to forget anything. So kind of like if you get a corruption for like one message on disk, and you say that, hey, actually I get a corruption, so let's pretend that I haven't received this message, you might actually violate safety. Your consensus algorithm might be broken, which kind of like is important for practical systems, because yeah, kind of like kind of like to rephrase this, consensus algorithms have a reasonable model of network failures. They assume kind of like they assume very little about networks and allow all kinds of failures and deal with that. However, consensus algorithms generally don't have a reasonable model for disk failures. They assume that disks are perfect, while it is not the case in practice. Well, kind of like you could make disks like almost perfect by using RAIDs, by like using many disks, by using like very expensive disks. Although kind of like the perfect here is like still depends on like the amount of time you store the data on these, because well, kind of like with enough time, like everything goes. But anyway, you kind of like you could push this reliability boundary on this kind of single machine, but that is costly, and that is wasteful, because wow, you have a whole cluster of machines, and the cluster, each machine in the cluster stores more or less the same data. So what you actually can do is that, hey, if some data is not good on disk of machine A, it can actually ask machine B to replay the data for it, so that durability is restored. Like basically, you don't want to waste durability. You don't want to require that nodes are more durable than they need to be, given that we already replicate the data across the cluster. So anyway, the point being, terminal assumes that disk fails. What does it mean? Well, imagine you're a replica and say you crashed, and now you restart. And now you restart, and the first thing you like go and read the data on your disk. And well, it might be the case that you're like reading a prepare that you have written while you were online before, and that prepare was actually gone. There's no prepare anymore. And that's like another reason why replicas might have holes in their log. That at some point in the past, they had this prepare, they wrote it to disk, but once they came back, the prepare isn't actually there. There is like a checksum mismatch. So let's maybe look how that actually works, like how replicas deal with holes in the log and how it gets repaired. Again, I'm not sure what's the best order to study these things. So let's just dive right in the middle. And let's start with on request prepare. So request prepare is a message that a replica sends when it wants to get a prepare. Let's see what is inside this message. Message type, okay, I need to look at the header. Request prepare. Okay, as usual, for message itself, we have like the checksum, we have the checksum body, and I think the checksum body, yeah, the checksum body should be equal to the checksum of an empty body because this is a header only message. It doesn't have any body. And kind of like nice tidbit, checksum of an empty slice is not equal to 0. So kind of like it's kind of trivial typography bug that you assume that if you like checksum something, you get 0, but that's actually not the case. Right? You're not going to get 0. You're going to get something, like random number there. So okay, for a request prepare, we actually assume that the checksum body should be equal to empty. I'm actually wondering why we are not, just doing this right here. Anyway, maybe we want for every message to like actually set the checksum. Okay, and then in the header still, this request prepare includes information about the prepare. It includes the checksum of this prepare, and it includes the op number. So again, op number is the number of the prepare in the log. And essentially, kind of like the whole consensus thing is about assigning those op numbers. And I think we've seen this kind of like crucial things in. Let me see. Let me show you this like supermoded line. Okay, pipeline prepare. Like this is the code where primary receives a request from the user and it converts it into prepare. And the main thing when we convert a request into prepare is that, hey, we assign this iteration number. This primary decides where this request is relative to all the other requests in this particular view. Okay, so yeah, this is our request prepare, basically a checksum and an op number. How do we handle it? On request prepare. Let's see. Okay, we get a message. This message is request prepare. We might be ignoring it, and it sort of seems like we actually should never be ignoring on request prepare. Well, actually, let's see. Interesting. Yeah, it looks like you actually do have some cases where we ignore request prepares, and this seems a bit odd because, well, kind of like the thing is you always request prepare with a specific hash. So kind of like it is always safe to reply to this event because to this request because the caller already knows the hash of the prepare. And as such, like if you send the data and the hash matches well, then that's correct. Like there's no like I don't think that there should be any reason for us to actually ignore this request. This is funny. I will ask my colleagues why we're doing that if I don't forget this. Uh, okay. So anyway, if we didn't ignore this request, which probably is the common case, we are going to, well, first of all, find the slot in the journal. Again, the journal is a ring buffer. This goes back to that replicas about checkpoints and replicated state machines. We cannot store infinite amount of messages, so periodically we need to do checkpoints. And because in target everything has a known limit, we actually know exactly how many messages we store, and that is journal slot count. So our journal is a ring buffer of messages on disk. It is persistent journal of exactly this amount of messages. Okay, so we get the slot, which would basically be just the op number modulo the size of the journal. Well, okay, let's check. Slot for all. Yeah, exactly. I guess it's right. We just model divide by slot count. Okay, we get our slot. Then we actually, it's interesting. Well, yeah, I guess what gave me a count here is that in target style we have a rule that hey, we don't declare variables in the narrowest possible scope. So it would make sense to kind of derive slot here because we're using it before, but actually kind of like all those three op, checksum, and slot are interrelated, so it makes sense to declare them here. So you kind of gather a slot, but you won't be using it immediately. First, I will actually check whether we have this prepare in memory. So maybe we are a backup, or maybe we are primary, and we just happen to have this prepare in our pipeline. So we go to our pipeline with a specific operation and a specific checksum, and say, hey, do you have this prepare? And let's see. So if we have a queue, and actually, I think, well, I guess, I don't know what the cache is. The queue is the thing that exists in primary, which kind of tracks prepares. The cache, I think, is something that exists on a backup, and it only exists exactly for this use case of repairing prepares. So kind of if primary repairs prepare, it should just write it to disk and then forget about it. Well, actually not. So okay, so let's say you have it and you receive prepare. So you need to write it to disk, but then you also need to execute it. And because everything is pipelined, you might not necessarily be able to execute the prepare right after it was written to disk. So you might need to kind of hang onto this prepare until you received all the previous one, and the cache is probably the place where you are storing those. Okay, but let's look at the case of the primary. So okay, in the primary we kind of look at the head, the tail of our queue. If we are in bounds, then because queue is a ring buffer, we can just offset at a specific index and get our prepare. And if the checksum matches, then we return it. And again, it is not guaranteed that the iteration and the checksum match because, well, the prepare might actually not be committed. So kind of in view X, one primary decided to commit a sort of prepare for op92, but then view change happened. And now we're actually in view X+1. And in view X+1, for that same op, we actually decided to commit a different prepare. So, well, this happens. So we should always kind of we never ever refer to a prepare just by the iteration. We always check that the checksum matches. Okay, so kind of like you can get prepare from the queue, and similarly, I think we could get it from the cache, and the cache is probably just some kind of a hash map. Well, no, it's also array, and here we also can do just direct indexing into our pipeline cache. Okay. So anyway, first case, someone asks us about prepare. We found the prepare in our memory, and we went ahead and sent out this prepare to the requester. And again, like you see, like there's like cool thing here is that we resent exactly the prepare we received. We do not attach any bad information here, like, hey, I'm replying to this particular request. No, we don't care. Like we try to reuse messages as is. Like replica wants to prepare. Well, kind of like here's the prepare. Like we don't like, and kind of like when the replica receives this prepare, it actually wouldn't know that whether it is a response to the prepare request or maybe this is just us trying to proactively replicate prepare there, or maybe even like it's not us, it's like someone else is preparing. The prepare itself, it doesn't say who like is sending this message. We don't care about this. Anyway, that was a good case. We already have prepare in memory. We are not always this line. It might be the case that prepare is on disk, and then we go to our journal. So what happens in the journal? First of all, we look at the prepare inhabited array, which says that we have something at that slot. Because well, if we are just starting, or if that slot is corrupted, we might actually have nothing at that slot. And if we don't have something at that slot, we definitely don't have anything at that op. Because again, slot is op modular journal slot count. So a single op maps to a single slot, but a single slot maps to infinite many ops. And that's why after we figured out that we have some prepare, we actually go and check the checksum of that prepare. And this is crucial. So journal is on disk. So the actual prepares are on disk. And okay, I dropped out again. Again, not sure what's happening with my internet connection here. Sorry about that. And I will be on YouTube. Okay. Anyway, listen to it because this is actually crucial. So let's go. Journal is on disk. So we know that hey, we had this prepare on disk. But we don't have immediately, but you don't immediately have this data in memory. You actually should asynchronously go to disk and read it and blah, blah, blah. What we have in memory is actually the checksum of the prepare, because prepare is like 1 megabyte and the checksum is like 16 bytes. So we could just store all the checksums for all the prepares we have in memory. And if we look at how we initialize this prepare checksum, this is a slice of checksums, U158 of length slot count. Pretty easy. Okay, so we check that we have some prepared a slot, and that we actually have, or we think we have the correct one. The prepare with this checksum. Okay, does it mean that we've won? Not really. The thing is, well, prepare is on disk, but we have a storage fault model. We actually don't know whether we will succeed reading it from disk. Maybe we will read it, and there is, some garbage there, and not actual prepare. Like maybe everything got corrupted. So we need to deal with that. Let's look at this. How this actually works. Okay, so Okay, I don't actually understand this command, but probably it's not important. Famous last words. Let's see how we read the prepare from this. Okay, so again, this is reading from disk. So this is asynchronous, and that's why. Well, actually, I changed my mind. We are not going to look at read prepare right now. We'll just note that this is asynchronous separation because it needs to fetch data from disk, and that's slow. And that's why it accepts a callback because, well, in Terminal, all our asynchrony is done like the old school ways via callbacks because callbacks actually are like good enough, like simple enough model for the amount of asynchrony we have here. And next thing here is that by looking at the signature of this method, we kind of like can understand what happens inside. And well, yeah, we see that we accept here an optional prepare message, and this option handles the case where prepare isn't on disk, where it is corrupted, the checksum mismatches, or whatever. And we also have like this destination replica. So destination replica is just the number we passed into the original read call over here. And this number basically tells us to whom we should reply. Because again, as I said, kind of like prepare doesn't really say what is the origin of this message, but request prepare actually has this replica. Okay, yeah. Actually has this. Let's see. Yeah, I actually has this replica number which says here like I'm requesting is prepared, so please send the reply to me. So we need to pass it here, and we need to get it there. And this is kind of like because well, not only we use callbacks, we actually like use function pointers and not closures because Zig doesn't have closures. So kind of like in high level language, you would actually close over this replica, but well, here kind of like they will have to pass everything explicitly as if we are programming in C. Likely we are programming in Zig, not in C, but still some things never change. Okay, so we got a prepare or nothing. And if we get nothing, like prepare is corrupted, well, we just do nothing. We just return. We don't even reply to that other replica saying, hey, we don't have your prepare. We just ignore them. And that's okay, because, well, after some time, they will retry requesting prepare from someone beside us. So kind of like, in this like distributed systems, you kind of like, you really want to kind of like be very kind of like chill, very calm. You don't want to kind of like frantically run around through the network with messages, like double checking that all the work you wanted to do has actually done, because well, you'll never know. Like there is like fundamental absence of information. Like messages can get dropped and whatever. So kind of like you want to get is like eventual consistent. It kind of like even if you are build like strongly consistent data model, like we do technical, kind of like internally there's going to be like this like eventual consistency style thing. Like eventually someone somewhere will probably get this message to that poor replica. Okay, so yeah, if we are unlucky, we just ignore them and they will hopefully retry. And if we actually have to prepare, then, well, we just go and send this message to replica. Okay, so how do we actually go and read this from this? Let's dig in. Okay, let's look what we have here. Again, we recalculate our slot. We double check that we have this prepare. Well, we double check that we might have this prepare because like it doesn't make sense to read this particular prepare with this particular checksum from this if we know that something else is there. So kind of here's like one-sided error. We kind of like we hope that it is there, but it still might get corrupted. But we must ensure that there is at least hope of finding there. Okay, if destination replica equals none, we check that we have more than one read. Okay, I don't remember what is like destination replica uh, equals down case means. I guess that's for recurring calls. Let's ignore it. For us, we know that like, destination replica is not now. Okay, so as usual, prepare is a message, and we want to read it. So we request a fresh empty message from our message bus. And again, if we go back to our constant, which limits the total number of messages, there should be something here. Actually, that's okay. That's interesting. I'm not entirely sure that this message here is fully accounted for because, well, we have this journal reads and journal writes, and I think those should kind of like account for this prepare, but we actually, we check for it's available only here, so presumably this one is actually a maybe, and then we get this message, and it is not counted by these journal reads. Okay, that's interesting. Uh, let's see. Well, let's see how it works. Either it's a bug or I'm not understanding something about this code. Okay. Okay, so the first case is that, well, before I said that we keep checksums in memory. Well, it's not actually exactly true because not only we keep not only the checksums, but we actually keep all the headers. And yeah, and you might ask like, well, why we have both checksums here? Okay, so okay, I get lost. Let me roll back here. So okay, yeah. So we have like this prepare checksums, which stores the checksums prepares, but we also have somewhere here headers, and also headers redundant. Well, okay. I was okay. So looks like we actually storing this information 3 times in prepare checksums, in headers and headers redundant. Well, no. Okay, so headers. Please ignore headers redundant. That's kind of like that's like something completely different. Uh, so look at like headers and prepare checksums. So I think what is happening here is prepare checksums is the prepare that is currently on disk. And the header is what we want to be on disk. So when you write a new prepare at an old slot, you first update the header, then you actually go and write prepare, and only then you go and update checksum again. Not ready to say if this is like true or not, but like I think roughly the idea was here. Okay. I wonder if there is some comment here. Here's okay. There was comment here, but okay. Anyway, let's continue. So, and why the stack? There is one case where we want to read the prepare, but the prepare is actually empty, which is kind of, I think, weird because I don't think we actually have any empty prepares. I think prepares are always non-empty. But anyway, if it so happens that prepare is actually empty, the body is empty, we could go and just use our in-memory header instead of reading prepare from disk. So we copy a message to the prepare, and then we memset the body of the message, and invoke our callback with the message. So again, that's kind of like the case where we have empty preparing boring case. Interesting case. We don't have prepare in memory. Then, okay, ignoring destination replica equals null case, we check whether we actually have this, whether we actually, okay, I think I got, I think actually I got what counts this message. This is exactly this thing we called burst. So kind of like something which, so yeah, I finally understood how to properly explain what burst is. So everything is asynchronous. There is this event loop which invokes callbacks, and everything except this burst counts the messages which are there in between event loop iterations. So while event loop waits for a particular callback to fire, these are all the messages that could be in flight. And then while we are executing a callback, then we could spend at most one extra message. So burst accounts for this. And kind of like when we actually start sending the message, then we will store it in send queue. There's somewhere should be send queue. Yeah, we store it here. So okay, so kind of like this will go from burst to send queue. Okay, there is no. Okay, let's get back here. So we figured out that, hey, we really gotta do our work. We really gotta go to disk and read that thing from disk. To read this, we need an input-output operation. Well, what is I/O? Well, it's the same thing as a port in TCP. It's not like someday, like physical reading head on your hard drive or something like that. No, it's kind of like a logical notion of a read operation in flight. And the thing is that we just bound the number of read repairs that we could do. So we have this configurable constant, which says how many concurrent read operations a journal can do. Then we have a requirement on the number of reads on the commit path, which again we'll get to once we get to commit path. Anyway, so kind of like we set aside, and we always want to keep 2 reads available for commits so that commits can never block. And all the other reads is what we can spend for prepare. So we prepare with open checksum. If we don't have a read, we just send a callback with null, which is exactly the same thing which would happen if the message is not there. So we even don't, again, this is beautiful error handling. There are completely different error conditions here. Either the message is corrupted on disk, or we don't have spare read IOPS, we don't have spare resources to read this message. But the caller doesn't care. The caller can't care which one is the case because in both cases you just invoke the thing with null. So that's, like, when you do error handling, like your natural instinct is to be very verbose about your errors, to precisely specify all the conditions which happen so that the core can, automate. But that's a good error handling on the micro level. On the macro level, you actually want to do the opposite. You want to think about, like, what is the minimal amount of information that the caller actually needs to automate, and can we make it abstract? Can we make core not care about errors? And here, yeah, the answer is true. Because we know that the other replica which waits for our repair is going to just retry. We don't need to do anything. We could just ignore them. So that's why we handle two cases the same. And that is beautiful. This also means that we increase the amount of testing of our code because we don't have two different code paths to test broken repairs and repairs which run out of resources. If we test one code path, we automatically test in the second code path because they are the same. That's kind of like the beauty of nicely designed error handling. Okay. So, we are out of reads. We say, hey, kind of like, please, we first log something to our log, like I didn't know product had log, but like actual log file we should tail. And then continue with our lines. Okay, so otherwise, we say, hey, actually, there is this one read in flight. We assert that, hey, we haven't committed too many reads, and then we actually start it. So first of all, we acquire. Now I don't want to look at acquire. I want to look at the reads. We acquire a read. What is a read? Well, it is kind of like, I've said that like Zeek doesn't have a closures, so read in some sense is a thing which stores all the things that the closure would be storing. We store a reference to ourselves so that in a callback we can find this journal back, so this is basically not interesting. We set the completions that defined, and I don't remember, I think, have we already covered our I/O loop completions and all that stuff? I think we did. So kind of like, yeah, basically inside our I/O uring, we arrange all in-flight iterations into an intrusive linked list. And for intrusive linked list to be intrusive, you need some space in data structures to store those pointers. And this completion is basically that memory for, completion is basically that memory for intrusive pointers. Okay, then we store the message, the callback, and the callback, the callback is like the callback that our core passed to us. The iteration, the checksum, the destination replica, and then we ask our storage to read into this message from this story, from this zone. So again, let's go to zones back a little bit. Prepares. So the storage of target node is a single data file. This data file is cut into zones. So first is superblock, then while headers, then while prepares, and blah blah blah. So this while prepares is like this zone, and this zone has a comp time offset. So we can like say, hey, kind of like while prepares starts at like, I don't know, 10th megabyte of our data file. I don't know actually what the physical offset is. And then within this zone, we calculate the offset for this prepare. This is a ring buffer. And we already have the index into this ring buffer, so a particular slot. So the offset here would be the size of prepare, and the size of prepare is the maximum size of message, which is 1 megabyte, multiplied by this slot. So again, this is why I love systems programming. Like it's so easy. Like it's like I don't know, programming 101. Like the baby code you write when you're just learning to program. Like, hey, you have an array of items, and like each item has like this size, and what is the index of like nth item? So you just take the count of items and multiply it by item size. Yeah, this is simple program. It's like it's really easy. It's like much simpler than do like front end, back end, React, SQL, whatever. Anyway, so yeah, it's like systems programming is like really for people who can't do front end. Like if you can do front end, like you probably you do the front end. But if you don't have this gumption, this capability to deal with all this complexity, you go to systems programming because that's easy. Okay. Well, we just go and read data into the buffer. And we'll see. I wonder, yeah, and I think well, actually, let's see what's the contract of read sectors. So it receives a callback, and how do we know whether we read something or not? I guess we just don't know. I guess the caller should, yeah. So again, somewhere here should be that bit of code which checks that the prepare hasn't dropped. That the checksum of this or this is actually the checksum that we expect. And looks like it should be somewhere here. Okay. Where do we calculate? Okay, yeah. Okay, so here we'll be like checking the checksum of the body. So let's actually try to read through this whole thing. So okay, we ask our storage to read some specific part of our data file into this buffer. And buffer is part of the message, and message is stored inside the read. So the storage called us back with this read. So out of this read, we can, which is like this completion thing, so this kind of like low-level read which doesn't know anything about the journal, we can use field parent pointer to extract the read for our journal. So kind of like that, that read which journal. Yeah. Okay. Yeah. This. I guess if I point my finger into display, it doesn't really work. So let me point with my mouse. Yeah. So this read. Okay. And from this read, this read stores a journal, so we can get back our journal, which is again kind of like ourself, like this journal. Because again, kind of like this is again, you don't have closures, so kind of like what is self? Well, you gotta create your own self. Yeah. So okay, we gathered everything together. So this is our old, this is our callback. Well, again, two callbacks. So one callback is that the callback that the caller, passed to us, and that callback expects a prepare, and then we are inside a callback which we pass to storage, and this callback expects just like a slice of bytes. So this is where we kind of like cross the abstraction boundary. We read some data from this, and now we need to, pardon me, my wordplay, to prepare a prepare out of that raw slice of bytes. Okay. So, well, first of all, if we are if storage called us back, that means that the read have finished, so we can decrement the amount of reads in flight. And then we can actually release our read data structure into IOPS. I guess next time we should probably take a closer look at IOPS, but well, next time. Next time will be next time. Okay. If that's actually interesting. So kind of like we already prepare, and it turns out that it was actually like further ahead than the op we have. So probably something was truncated. It's I guess this was suspicious to me because well, kind of like if someone asks us to prepare with a specific checksum, well, we should just send it to them without like thinking about ops or whatever. But well, anyway, probably like it doesn't. Again, so well, right in the head again. In our consensus, because there might be a view change, it might be the case that like some prepares are actually truncated. And I think this case could happen when we truncate. So someone reads, someone asks us to repair a message in this view, and then view change happens, and then we actually truncate this message. We say, hey, this message is no longer part of the log. And that's why we kind of like realize that actually it would be wasteful to try and send them this message. Which again, it's true because well, like if you know that this message is useless, you might not want to spend network resources sending it over. Okay. So some extra. Well, again, kind of like this is a similar case. We didn't truncate this prepare, but like we replaced it with a different one. So again, kind of like out it goes. Okay, then kind of like well, the first then you actually start checking the checksum. So the first thing is that well, we really prepare. So prepare has a header and a body, and the header carries two checksums. One checksum covers just the header. The other checksum covers the entire thing. So we check the checksum of the header, and if it is not valid, well, then we get a corruption, and again we invoke a callback with null. Otherwise, well, the checksum matches, so the header must be correct. So we check that like all the basic invariants of the header are also correct. And as a reminder, well, maybe not as a reminder, maybe this is the first time we are seeing this. Okay, let's look at prepare. Every header has an actually every header has an valid method which checks like basic invariance of validity about this message. And because we verify the checksum, we can assert that this is right. And again, this is kind of like slightly iffy because well, if someone's like really malicious, they could have written some garbage into that disk, into our disk with correct checksum. So kind of like if someone like really like writes intentional garbage into the disk with the correct checksum, we'll fire this assert, which is like again okay, because well, it's what happens. We really want to like really shut down the operation because like someone is tampering with our disk. We don't guarantee that we detect all the tampering with disks. Like we assume like non-Byzantine non-visited scenarios, but like again, well, there's like some proverb here, like about caution or whatever, but basically kind of yeah, trust but verify. If we can shut down, if something bad's happened, let's try to shut down. Okay, anyway, kind of like another sanity check. We check that like the cluster is the same that we have other, and like this tries to protect against kind of like really weird scenarios where like you run two target vittles on the same hard drive, and due to some hardware or software failure, a write of the first target vittel actually ended up right into the disk of the second one. So kind of like we check, hey, this is not the, if that's the case, let's also kind of like shut down. And then, yeah, and now kind of like we read and prepare from a particular slot. Well, why slot is well, okay. We are running out of time, so I want to kind of like quickly run through this so I don't fully understand like this error condition, but yeah, basically kind of like this something that happens. Then, hey, this is not the prepare you're looking for. So read the message, and what we read has the correct checksum, and it looks reasonable, but like it is self-consistent. But it's actually not the thing that we are looking for. So again, we return here next. Well, let me maybe spend a couple of minutes talking about this. So the case is here is like misdirected read or write, and this is important. So if you think about like error conditions of disk, like if you assume that hey, disk fails, how would you like think about failing disk? Well, you would probably think about it, hey, it's just like flips some bytes, or maybe bits or something like that. So kind of like like local error. But that's actually not the case. That's not the only possible error. The really bad error is when something is misdirected. So like, data which should be at a particular offset of disk ends up at a different offset. And again, this actually might happen due to hardware and software errors. And that's why kind of like this like very deep property of the code is that when we read something from disk, we always compare it against a checksum which we got from elsewhere. Like because if you read the data and you check the checksum against the checksum which is part of the data you have just read, you are not protecting yourself from misdirected writes. Because, well, it might be just, the data might be self-consistent, but it might be from a different part of the disk. So like you always need to double check. You need to check that the data like is self-consistent, and then you need to check that it is that data that you want to. So that's why kind of like here we check that the checksum is self-consistent, and here that the checksum is much of the checksum that we wanted to get. Well, finally, as a very final check, we check the entire body, and this is like we do this last because checksum in the entire body is slow, and and if we are not going to respond with the message, we don't want to waste our time checksumming the body. That's why also kind of like having checksum in the header is useful because well, if something is like completely corrupted, you can very quickly tell it. Okay, so again, if body is broken, well, we can return on, and finally we reply to the callback. Actually, like, I don't know. I covered like 10% of what I was planning for today, which is good news. That means that we are going to have quite a few more episodes of Final Video. So let's recap what we've looked at today. And actually, we looked at just a single thing. The fact that the local log of a replica might be incomplete. There might be holes in there. And we were looking at, well, how replica tries to fill these roles. And like, well, we looked at just like one kind of like one aspect of this, how replica tries to help other replica to repair a particular repair. Okay, yeah, I feel like I'm like speaking in circles already. So let's make a pause here and see you next week, where we will look at kind of like the thing which drives this whole repair process in the cluster. Thanks for joining us today, and see you soon.